Thank you very much. It's a great pleasure to be here. Thank you for inviting me. It's nice to be back in Bengaluru. So my talk is going to be not exactly off topic, but not on the same topic that I've been listening to. This is actually about two-dimensional engineered materials, but the engineering is done with photons. But the main point of this talk actually is not even about that system. It's about the physics you can learn by using non-equilibrium systems to discuss non-Hermitian dynamics, non-Hermitian, non-reciprocal dynamics. And in general, what I want to point out is that you lose that you lose reciprocity when you have non-Hermitian dynamics, and I'll explain why. But I need to warm you up on the topic. And I'm going to be talking about Bose condensates made out of photons. But my view of these is a very simplified one. I think of them as synchronized oscillators. And let me give you an example of synchronizing of oscillators. This may be one you've seen, but even if you've seen it, please pay attention because it will has a point to it. Here we have two nonlinear oscillators, metronomes. They're both set to 208. As you can see, they're beating more or less at the same rate, but not exactly the same. They're slightly out of synchrony because it's really impossible to get them accurate. What I'm about to do now is to actually find a way of coupling them. We're coupling them by putting them in a cavity. The cavity consists of a shoebox and two soda cans. And you can see instantly the effect that they have actually synchronized. And notice that the synchronization is accompanied by an oscillation in the cavity. And these are moving together. The system that I want to talk about, polariton condensates, are simply a quantized version of this. Polariton consists of an exciton, which is an oscillating two-level system from my point of view. So quantize those metronomes. That produces an exciton. Let's imagine there are more metronomes. And they're coupled together by exchanging energy through photons in a box. And here's the box. But this experiment has another point to itself. But of course, it's an experiment about synchronization. It turns out it's a very old one. I didn't want to do that. There we go. This experiment was actually done several hundred years ago. I should check, actually, who in the audience knows who this is. Famous 17th century physicist, not Newton. Any takers? Huygens, thank you. This is Christian Huygens. Okay. And he became a Fellow of the Royal Society, I think the second foreign Fellow of the Royal Society. And he had a research grant, actually from the British monarch, through the Royal Society, to build clocks. You know, for obvious reasons, so that the British could build a navy, travel around the world, and arrive in places like India, actually. So, you know, he took the money, he built some clocks, and he sent a paper to the Royal Society, communications to the Royal Society, and this is an excerpt of the paper. And in the paper, he reports synchronization. And this is part of actually good experimental technique. This is from his lab notebook, if you like. These are two pendulum clocks. He built them together inside a common frame. Of course, why did he build two? Well, he was trying to build very accurate clocks. There was no other way of telling time other than to wait for the sun to come overhead every 24 hours. And that's a bit slow. So he decided he would make two. He would let them beat, and he'd be able to judge the error in the timing by the fact that they wouldn't beat together. So he was a little bit surprised to discover that sometimes when he set this thing up, they actually synchronized. And so he reported this synchronization. It's interesting, however, that they synchronized out of phase, synchronized this way. And he was a rather smart scientist. he deduced that they were coupled by what one would call imperceptible movements of the common frame supporting the clocks. So he had two oscillators synchronized by phonons. And he was sort of ahead of his time, actually, in terms of a classical model of superconductivity. But for those of you who've gone into the innards of BCS theory, by the way, BCS theory is actually just a theory of coupled oscillators. If you look at the equations of BCS, they're identical to the equations you would get by coupling oscillators together. Now, but that leaves a problem. I mean, I'm not a very good experimentalist, but I didn't get his answer, right? So now, of course, the form of coupling that he had is very different from the one that I had. Coupling was inertial. This coupling is presumably not. It's elastic, some other degrees of freedom. So what goes from one to the other? And in fact, we know, this has been a very well-studied problem for a long time, that, that this system, you can tune parameters in the model, changing couplings from elastic to inertial, and you'll get a transition from in-phase to out-of-phase. And the question you might ask is, how does that transition happen? It looks a bit like a ferromagnet to an antiferromagnet. And as we know, in a statistical physics problem, you can go directly from one to the other. Or occasionally, if the temperature is high enough, you'll go via a disordered state through a paramagnetic state. Or is there another way? And of course, I wouldn't have set you up for this if there wasn't another way. And this is the way. So generically, the transition from one state to the other state will happen via an intermediate state, which is chiral, so-called PT symmetry broken. And the way that it works, you can describe it here. Imagine I start on the right-hand side, and here's some parameter which I can tune to go from an aligned phase to an anti-aligned phase. So while I'm sitting here, everything is locked together. But as I tune in here, all of a sudden there's an instability, and the instability is such that these things move a little bit out of phase. Not much, but a tiny bit. And that actually starts to rotate round and round in the rest frame. And so there's a broken symmetry of that rotation. It's chiral. Sometimes it goes right, sometimes it goes left. You don't know in advance. As you tune further, they get further and further out until eventually they lock again in the anti-aligned state on the other side. Another way of looking at this, which we're used to, is to think about the eigenmodes associated with the stable and unstable states. If you start out on the right-hand side, there's always a Goldstone mode, because you don't know the origin of time, and therefore you can always change the overall phase of the pair of oscillators. And then, of course, there's naturally another mode, linear mode, which is you could call the clapping mode. Take these two oscillators and push them a little bit apart, and they will ring back down with an eigenfrequency. That's a so-called Lyapunov exponent. That will be damped. And that damp mode softens and hits a critical point. And at critical point, you actually have two degenerate eigenmodes. And that produces this instability. And this has a mathematical name. It's called an exceptional point. Exceptional point is just a point where if you have a matrix that you can't diagonalize, of course, that requires the matrix to be odd in some way. This, of course, is a non-symmetric matrix, and that non-symmetric matrix doesn't have to have, is allowed to have degenerate eigenvalues at special points. So here's an experiment done actually with polaritons. I'll run through this just quickly because I'll tell you a little bit more later. And what you're looking at here is you're looking at the light emission from two Bose condensates. So the reason that I know that these things are Bose condensed is that their energy emission is very sharp. Think of them as lasers. There's not much distinction really between a laser. There's a trap, so that there's one here and there's another one there. They're a few microns apart, but they're coupled. There's actually a Josephson coupling between them. And that Josephson coupling can produce states which are locked. And you can see that these two things are more or less the same, although you notice that there's an occasional fluctuation up here, which I'll come back to. As you drive it over here, in this case, it's not going to asynchronize, it's going to unsynchronize. There's been some parameter change in here that's got you to a disordered state. But in between, if you look at this frequency spectrum, it looks really rather ragged. There's points which are relatively sharp, and there's bumps around in between. And these authors, actually not us, interpreted that as a frequency cone, which is basically associated with a mixing of the two sets of frequencies. And I'll talk more about this. So that's sort of a warm-up. And the fundamental question I want to ask is, can I generalize that low-dimensional system? I talked about two oscillators to something where there are many oscillators, spatially extended. Is this critical point analogous to a thermal phase transition? And can I do theories about that? Does it come decorated with fluctuation dynamics? Is there some kind of universal theory? And by the way, is there any kind of connection between quantum systems, which I just talked about, like a laser, and synchronization in classical models? And I'll partially answer, I think, most of these questions. So now I need to tell you about polaritons, because I don't think anybody has spoken about this, and I'll be very oversimplified in this. So as I said, imagine that what you've got is that you have a semiconductor. You've excited in that semiconductor a large number of excitons very near the band edge, so it's relatively dilute. I'm going to treat those excitons, as theorists like to, as two-level systems. Either it's empty or it's excited. It's just a two-level system. It's either there or not there. I've got a bunch of sites. You can make this more accurate, but this will do. You put this system in a box with mirrors, and you choose excitons that are optically active so that the excitons can exchange energy with some photon mode. And you also try and tune the mode in the cavity to be pretty close to the energy of the excitons and let them hybridize. So what does the spectrum look like? You start, and now I'm actually going to deal with a two-dimensional box. So here, in fact, these systems are all quantum wells. They're in 2 dimensions, and there's a mirror on either side of a cavity, so it's a 2-dimensional cavity. Very simple. In that case, the cavity modes look like this. This is the photon dispersion, energy versus momentum, momentum being the momentum in the plane. And this is just, of course, a section of a light cone. Whereas excitons, so this is the velocity of light. Excitons are pretty massive and are essentially flat on this. And if you're good at this, you can engineer the system so that these things are tuned to be close to resonance. When you couple, you get a mixed mode. And these are called polaritons. The splitting is the Rabi splitting. That's the dipole coupling between the photon and the exciton. And you get 2 branches coming in here, so-called lower and upper polariton. And these correspond to the in-phase and out-of-phase modes of that system of excitons and photons. So it's many excitons, very few photons. So now these objects are basically bosons. And one of the reasons that they've been of interest then, yeah.
Is that dashed line correct for the photon that you have got? Or should it be a parabolic dispersion?
It's just because I've got a cavity, and therefore I've got lambda over 2 in one direction, and the dispersion in the other direction is here. So you take the light cone, which looks somewhere like this, and I take a section of that light cone somewhere here, corresponding to a wavelength in the z direction, which is 2 over lambda. And therefore, the intersection here is now a parabola. Thanks. No, it's important to make that clear. And so the nice thing then you see is that by tuning the thickness of the cavity, you can make the cavity to be resonant with the polariton. So that's harder to do than it looks. But then the next thing you could do is, well, suppose you can now excite polaritons in the system and let them thermalize, but not let them decay. So if the mirrors are very good, you can create excitations in here and they'll live for a long time. They should thermalize inside the box and they won't escape. With luck, they'll sit at the bottom of this distribution. And of course, they're really essentially bosons, at least in the dilute limit. They're bosons that have a very light effective mass, because the dispersion here is really given by the dispersion of the light cone. But they're quite strongly interacting because they're 50-50 excitons. So they can thermalize very well, and they tend to produce, therefore, a high temperature condensate. And this is what it looks like. You can build up something like this. And so they collect in the bottom. There's a momentum distribution. And in fact, what you're looking at here is the light that eventually escapes from the cavity. So the distribution here near k equals 0, when it goes through the mirrors, if the mirrors are flat enough, doesn't lose any lateral momentum, so comes straight out. And so the angular distribution of emission tells you the momentum distribution of the particles in here. So that's the basic setup. And this has now been going for 20 years or so, and lots of things have been seen in this. So one can see things that look like BEC. You can now look at the dispersion inside the condensate and see that it goes from this parabolic dispersion to something which is linear. You can create vortices. You can look at superflow. Because these things are 2D, they tend to have power law correlations, BKT-like. And you can then also look at coupled condensates and many more things. So this is a nice story. I don't want to talk more about this because I want to talk about one very specific thing about which condensate do you have. So this is a two-component condensate. I have mixed light and matter. And I'm pretending that they're locked together in one or the other in the BEC, which is like this. So there's a nice minimum sitting here. Now you might also ask, well, if I could get a condensate here, why couldn't I get a condensate up there? In fact, I'll show you can. This is also quite stable. It's, of course, metastable, but it takes a long time for particles to escape out of these things, and so you can have a non-equilibrium BEC. And this is also a perfectly good condensate in the sense that it doesn't have infinite lifetime, but it lives long enough that it has all of the characteristics that you associate with a good BEC. The problem is that these two condensates have exactly the same symmetry. So just like the first problem I told you, there's a Goldstone mode associated with either the in-phase or the outer-phase condensate. That is the symmetry which is broken. But that symmetry is the same for here and here, and that's the only global symmetry. And to transition from one to the other is an internal discrete symmetry and is not associated with the broken symmetry. So you ask, well, how would I get from there to there? This is really the only way to, so I imagine I have two parameters which you can indeed tune, something like the pumping or the damping of the cavity. And I can change parameters and maybe I will see a jump from one to the other because they're really of the same symmetry, there's no distinct phase. But because they are of the same symmetry, there's no reason I can't go continuously from one to the other. This is very much like a gas-liquid critical point. There's no symmetry distinction between gas and liquid. Of course, a lot of the time you see a first-order transition, but there is a critical point, and you can go in a supercritical region around this. And that seems to happen here. But that has to be then associated with getting a very special values of parameters, so that at this point the two things have to be degenerate. And that means, of course, that if you look at the frequency at which these things oscillate, they would actually have to come together some way. So treating these things as if they are discrete states isn't really right, and there really is a continuum. And so this mode has to move up as they come close to here to join with this one and then come back down the other side. But then again, I have a system which has two internal degrees of freedom, and that point is marked as a critical exceptional point in the same way that I described it. So can one do this? We We haven't seen all of the details of that. You can certainly make upper polariton condensates. This is actually done in a TMD cavity. Many of the earliest experiments that were done on polariton condensates were done with conventional 3-5 semiconductors, which, because the binding energy of the excitons is so small, limits you to very low temperatures. By going to TMDs in cavities, you're doing essentially room temperature physics because the binding energy is so much bigger. And here, indeed, there's some experiments from David Snokes' group. Here's the dispersion. This is in the uncondensed state. Here's showing you crossing over to a condensate. Also, different sets of experiments. Here now is tuning pumping, shows a transition, and this is just looking at the intensity of the light going out as a function of some parameter. There's a threshold of onset, and then there's another jump. The frequency jumps in this case, so that looks like a first-order transition. It's not always does one see that. And as I remarked, the point is that the normal state is U1 symmetric, but these two states are both U1 broken. One of them looks a bit more like a laser, has many more photons, but they have exactly the same symmetries, and how can there be a transition? I think I already told you the answer. Here's a bit of the math associated with this. If you actually want to model this, there's lots of ways of doing this. One can go all the way to the microscopics, but it's natural to think about kind of Ghosh-Pidievsky equation, which is damped and driven. So there's pumping here in one channel, damping in another. Notice the change of signs, some nonlinearities. And there are special points in this phase diagram where you can see this jumping. I don't want to spend a lot of time on this, so I'll come back to this at some point and see where I am. A point I do want to make, however, is that if this is a critical point, it's going to look quite different from a conventional phase transition. So conventionally, if I have a phase transition, say for something like an XY model, I can often look at my order parameter. I have this sort of wine bottle minimum Mexican hat potential in the ordered state. So I've always got fluctuations which can run around the bottom. That's the Goldstone mode. And I would have a massive mode, which is associated with amplitude fluctuations. As the potential becomes flatter, that amplitude mode gets softer, and eventually both of the modes become soft at the transition, but they're orthogonal. It's a Hermitian system. At a critical exceptional point, I may have a potential that looks more or less the same, but actually as I go towards the exceptional point, the modes, in fact, become parallel. They become identical. So rather than having, a single Goldstone mode here, you actually have two. And that makes the fluctuations in principle a lot larger because there's a larger space of fluctuations to understand that. Okay, so let me run from that and entertain you with another video. So in doing this, we started off in quantum theory, and at Chicago, we do a lot of soft matter physics, and I have a colleague, Vincenzo Vitelli, many of you will know him, who likes to play with toys. And so we hit upon thinking about whether or not one could do very similar things in a soft condensed matter context. So these are robots, and in principle they move around, but we don't let them do this, we just let them orient. And we give them rules. We say red wants to align with blue, and blue wants to anti-align with red. So they've got asymmetric rules. However, we set them up to be coupled reciprocally, but they're anti-symmetric with each other. And then you let them go, and you ask what happens. And there's no external torque-applied, and they do indeed, for these parameters, break the symmetry and start going around in circles. If you repeat this experiment again, sometimes you get right-handed circles, sometimes you get left-handed circles. I should say it's actually a many-body phenomenon because it turns out if you have a finite number of robots, eventually it stops. You need an infinite number of robots to get this to happen. We could only afford 8, so I won't show you this for very long because it stops working, but one can check that. And now let me just show you some simulations of a different kind of model. This is bird flocking, but we've got 2 species of birds. We have red birds and blue birds. And we've set them going, and this is, I guess, an engineered system in 2 dimensions. And what you're looking at here is something where, if you like, temperature is high, and they're following the same rules, but they're sort of basically fluctuating around. And if you look at the average velocities, it's very close to 0. Whereas for a different set of parameters, we see them all aligned. Another different set of parameters, we see them anti-aligned. The direction in which you align or anti-align is also another degree of freedom. And as you go in between, you get this phase where you can see visually that they're actually flying around in circles, and here's the average velocity going around. So that's the chiral phase. So, yes? So the interaction is literally, sorry, so this is what's called a Vic-Sheck model. So, but what all that is that each bird looks around at its neighboring birds within some radius, averages their velocities and decides to fly with them or against them, depending on red versus blue. Well, so the red with blue, so for example, red wants to align with blue, but blue wants to anti-align with red. Right, so it's exactly the same model as we had with the robots, but just, right, so they've got, so it's not possible for them to solve that problem because they can't find a way of cooperating. Sometimes one wins if it's this, sometimes another wins if it's that, but in between you get this other thing. So this is the same picture that I showed you right at the beginning. Just to this, there's a regime where everything is aligned, some parameter where you can go from one to another. There's an instability where they begin to have this chiral instability that produces this rotational motion. And eventually the angle between them gets back to the other one, and they get into the anti-aligned regime. So it turns out that this is actually very general. There are large classes of models which have continuous symmetries. Models like this, which are sometimes known as contrarian Kuramoto models, turns out Swift-Hohenberg instabilities, where you go from a pattern formation, so this is pattern in space and this is in time, there's transitions to something where the pattern decides to start moving, either to the right or the left. It's somehow the same. And there's a general phase diagram for this. So that, in terms of parameters, I'll just say that I have a non-reciprocity parameter along here, which I can tune. Non-reciprocality equals 0 here is conventional mechanics. And in this case, I go from, if you like, anti-ferro to ferro, but everywhere else, I have a transition between them. And there are classes of models which are so-called PT symmetric, the kind I just described. And there are other classes of models which includes the polariton condensate, which are actually PT broken. And you can, for that, you need to imagine another axis, which is a bit like having a magnetic field. So the system, so in this case, if you're up in one level or down in one level, it knows the sign of the instability that it's going to have. So how am I doing for time? You can actually generalize this as well. It doesn't actually have to have complete symmetries. You can do things where you have limit cycles. So a limit cycle is a dynamical system which has something which has an orbit which repeats. The shape of that orbit can be quite complicated, but it is repeating. And there's a direction along the orbit where it has, if you like, the analog of a Goldstone mode. It doesn't know what the origin of time is. And similarly, you can have transitions with merging of limit cycles, which bring that in. I could talk more about that. This works for predator-prey models. It turns out one of my favorite ones actually is neurons. I'll stop here for just to comment on this. If you want to find a system which has built-in non-reciprocity, the brain is ideal, because the neural systems have two kinds of neurons, excitatory and inhibitory. And that's exactly the rules. Excitatory neurons make other neurons fire. inhibitory neurons prevent other neurons from firing. And so their dynamics is precisely this. And much of the structure that one can see in neural circuits, of course, is associated with having the possibility of forming a cycle which is self-sustained. That presumably has something to do with thinking. The alternative, of course, if things go wrong, is either you have something which is completely quiescent, which is death, or completely synchronized, which is epilepsy. And you sort of need to be somewhere in between. And neural networks are in fact balanced in order to do that. And so that's a sort of interesting way. I think I have a little bit of time to say something about this. Everything there I was talking about was really effectively mean field. For this audience, maybe this is useful. We again took this little model and put it down and did numerical simulations. This case is in one dimension, but adding noise. So here's a phase diagram I showed you before. There's a parameter that you're tuning, and at zero noise, you go across this line between a chiral phase and a static phase. And then we add a little bit of noise. And the moment you add some noise to this, you won't be surprised because it's a low-dimensional system. The order goes away. But how does the order go away? And the order goes away in sort of two different ways on the other side. On the static side, it really looks like a little bit of a one-dimensional ferromagnet. You add a little bit of noise, it generates some domain walls. The domain walls stay put. They don't do anything very interesting. And it disorders by a proliferation of domain walls. On the chiral side, you get a different answer. Because on the chiral side, when you nucleate a chirality, you started with a ground state which was, say, right-handed. If you make a little bit of a domain in the middle of this which is left-handed, of course the phase starts to wind up, and eventually it gets very unhappy and breaks, and so you get patterns associated with this. You can look at then what happens to correlation functions as you come through here, and you see a qualitative change as you go from left to right. So this is actually looking at some long-range spatial correlation function, which just for this purpose gets very big at this point, and we're cutting across at low temperatures. And what you can see is something which is very analogous to a quantum critical point. There's a well-defined critical point here. With noise, it vanishes. There are two crossover lines on either side. But as I pointed out, the divergence here is really much more substantial than it would have been otherwise. I want to leave a little bit of time for discussion, so I won't go through the numerics on that. Sorry. And then I just want to close with trying to get back to quantum systems. And so this really is an open question from my perspective. Is it possible to take more familiar systems that we work with in condensed matter physics and manipulate them to get some of this stuff to happen in microscopic quantum systems? Of course, you understand that they will have to be driven. You can't do this without being out of equilibrium. But of course, you also don't want to be out of equilibrium just by heating. That's not helpful. So you need some very precise way of building models for that. So actually, over the last couple of years, there's been quite a lot of theory working on this. I mean, aside from the polariton experiments that I showed you, which are in some sense cheating because they're very big macroscopic objects, here's a couple of proposals. And let me just describe them quickly. The model that one writes down for a polariton laser is sometimes called the Dickey model. It's two-level systems exchanging energy with a photon field. So this rather nice paper, by the way, these are not from me at all. These are both other groups. Sets up a system whereby you can have atoms of all of one type. You can excite, so this is really a cold atom experiment. You can excite optically to some third-level transition, so-called lambda-like transition, for those who come, where depending on whether you go down with left chiral or right chiral light, you end up with two different species of atoms. Let's call them sigma plus and sigma minus. and they're interacting with this photon field, but they're interacting in a way which has a kind of a synthetic gauge field.
Any bosonic.
It says these are all bosonics, right? Right. So with a synthetic gauge field, and you can build the kind of model that will do that. In principle, I think the ingredients to do this are sort of known. There were some experiments from Esslinger's group a few years ago demonstrating that there was sort of the basis of doing this. Here's a more recent one, actually, that I'm very fond of. Actually, this comes from Rio Hanoi, who was, by the way, the postdoc in the group on sort of the original piece of work. And this looks complicated, but I'll try and explain the background to this. This is really a kind of a solid-state physics example, but I just want to use it as a thinking point. And maybe one way of doing this is to imagine how would I take say a half-filled Hubbard model as an example. And because it's localized, then there are going to be spins, and normally we expect that they will be antiferromagnet on each side. How does the antiferromagnetic interaction come about? It comes about because, of course, this electron can hop to another level up here, which is level Hubbard U above that, and it can hop onto this side only if they have the opposite spin. And therefore, that lowers the energy just a little bit to give you this antiferromagnetic interaction, which depends on T squared over U. So suppose you have a core level in a laser. So what you can do is, in principle, you can pump this state. And you can pump it in a spin-dependent fashion. You can make sure it only gets involved from this spin and not from that spin. And by doing that, you can block this hopping. But you don't block that hopping. So in principle, out of that, you can get JAB not equal to JBA. No, this is a particular worked out example of that. It's all theory, but I think it's a very interesting idea, which ends up, by the way, in terms of dynamics, which would be Landau-Lifshitz-Gilbert dynamics for the spins, but with two damping and a non-collinear term associated with that. There may be other ways of doing this, and I think actually, by the way, that TMDs offer, in principle, a lovely system to tune this, because with TMDs, for example, you can always play with K and K prime, and you can pump, for example, the higher valley level, and therefore block various transitions and see if you can't induce various kinds of magnetism. And there's some experiments that show that you might be doing that already. But there's a sort of variety of things that one might do. And the nice thing, of course, about TMDs is you have very clean systems where you can hope for very, very long lifetimes so that you can get into the kind of regime where you can get sort of to equilibrium. But as I say, these are just proposals, and I'm very happy to discuss ideas with people. So here are my conclusions. The first one is that I think there really are classes of dynamical many-body phase transitions between different stationary states, things which are already synchronized, but have an internal degree of freedom to jump between them. And in between that, there are unusual states. Sometimes people would like to call these time crystals. These are a dynamical system analog of an exceptional critical endpoint, and they have, we think, although I can't be sure about that, probably universality classes which are different from thermodynamic phase transitions. This is actually easy to do in biology. Is it possible to do it in quantum systems? I'm not really sure, but I'll close with that. And thank you very much for your attention.
Right. Questions? Yep. Okay, so let's get started. As far as the quantum systems are concerned, I mean, you get the original examples of a quantum system in cavity, like, for example, TMDC, which is K and K prime, and if it's a pure cavity, there are several experimental evidences of polarity transformations in there, right? So, is there a way in which one could? So, are you saying that in order to introduce this non-reciprocity in a quantum system like that, would be to actually create an asymmetric coupling of k and k prime value to the cavity? Is that
I think that's one of the things that you could do, right? So the idea would be to find a way of doing that, but I think you need a little bit more than that, because you need, in some sense, having k and k prime not be different is sort of just a kind of a broken symmetry, like applying a field. Mm-hmm. You really need k to know that when it's next to k prime, it does something different than when k prime is next to k.
Okay.
Right. So it needs to be engineered a little bit more carefully than that.
Mm-hmm. Right. And that seems, I mean, when you say k knows when it's next to k prime and k prime knows when it's next to k, I mean, how does a solid state device knows that?
Well, I mean, so I suppose I mean, again, look, I mean, no, here I really have no idea. I say this is sort of a proposal, right? But no, build a moire. Maybe that's the easiest thing. So you have a pattern, right? Right. And so, there's a well here, there's a well there, right? And of course, they can be labeled by, under certain circumstances, whether you're dominated by k here and k prime there. Right. So you actually have a lattice which has already broken that symmetry. Right.
Okay. So that
right. So then there needs to be some communication between those two. Right. And as I say, the way that you can make them different is that k is spin up, say. Right. So the level above it is of the opposite spin, right? So you've got band which is looked like this. Here's k. Here's k prime. These are all supposed to be degenerate. Sorry, this is the spin orbit split bands, right? So so you can populate this state without populating that by using the right chirality of the light. Okay. Right. Okay. So by that you can really distinguish k and k prime. Okay. Right. But then you're going to have to deal with all of the relaxation processes, because of course this can decay back down there. Yeah. It can move along at high speed and produce an RKKY ferromagnet and things like that. So to be honest, I don't know. But what I will say is that for various models that one can write down, there is a well-established theoretical machinery for integrating out these spare degrees of freedom using Keldysh or various things that you want to do to generate dynamics. So with a model with parameters that one knows, you sort of know how to see if you're getting into the right kind of regime.
Yep. Anyone? Anything else? Yeah, Manish.
Well, I mean, in many complicated ways, well, let me give you the other limit of this, right? You can get to a limit where the excitation density is so high that the excitons dissolve and they become a plasma, but you can still have a condensate. We call it a laser. Okay? If you go to textbooks of lasers, they write down the same Hamiltonian that one does for BEC, right? And these are really two different limits of that problem, and going from one to the other involves thinking about decays, loss mechanisms, all of those things. So in those cases, so it really does matter. So it turns out that sometimes those transitions that I showed you to the higher pumped state look very much like a transition from a Bose condensate to a laser. Right? And then there can be other exotic things in the middle. You can make solids out of these. So I mean, there's a lot of richness associated with exactly that interaction, because they're not hardcore bosons, that's for sure. But in the dilute limit, they sort of look like it enough.
Any other question? Yeah.
Thank you for a very nice talk. My question might be too basic, but I had a question about that critical exceptional point you were mentioning. Yeah. So you had two branches, both of them had similar dispersion, like after that splitting. Then if I remember correctly, you mentioned at exceptional point, they become degenerate. Right. Do they become degenerate at k equal to 0 or at some other k?
Oh, good. Usually at k equals 0. It's possible to find situations, at least theoretically, where you have instabilities at finite k. So that's a very good question, because I mean, you can, like all of these things that we're used to, you find some mean field like critical point And then there are lots of fluctuations in the vicinity of that. And then you're sort of up for grabs about, do I have stripe order or do I have something else like this? I suspect that all of those things are there.
See, I was trying to look at it as like a two-level system, where I have this, so you had this one excitation which was almost dispersionless, and then there was one with dispersion. So if there is some coupling between them, shouldn't I get like a level repulsion?
Sorry?
Like, shouldn't I get a level repulsion, like anti-crossing kind of behavior?
Well, I mean, so of course, that dispersion that I gave you always has level repulsion in it, and I could never make a degeneracy. Of course, the real model has damping and loss. And because of damping and loss, then you can have situations where the levels don't repel. Right? And actually, the exceptional point is where you have level attraction. Right. So that requires you to tune very carefully parameters, to have that happen. But indeed, so this is, for those systems, it is entirely a consequence of being non-Hermitian.
Right. Yeah, thank you. So my other question was, I think it might be a little bit more general, but is it possible to get this kind of non-reciprocal behavior without non-Hermiticity? Like if your system is not non-Hermitian, like if you have a Hermitian system, can you still get non-reciprocal behavior in some situations? In quantum systems?
In a limited sense. So this model, because it's got two species, there are symmetries. If you look carefully, it turns out that M is plus or minus. If you flip the spin and you flip the phase, then it's the same model, so there is a symmetry. For each individual species, it is not Hermitian, but it is a PT symmetric model. Okay, so if you like, there really is a Hamiltonian. Right? For this one, there's actually no simple Hamiltonian that I can write down that will give you these equations of motion.
I see.
No, but it's a very perceptive question, because I think it's, so this is indeed an effective Hamiltonian, and if you expand the basis space of the operators you've thought, you can find some pseudo-Hermitian operators to describe it.
Okay. Yeah. Thank you.
All right. Yeah. Any other question? Okay. If there's no further question, let's thank Peter for it. Very interesting.